Hello, my name is Alex Gluchovsky. I'm CEO and co-founder of Meta Labs, the company behind the zkSync protocol. It's an honor to be presenting at the Global Blockchain Summit. And I'm going to be talking about some really hot topic these days, that is zk EVM. And we're going to go pretty technical on the details of zk EVM implementation, so bear with me. zkSync is a zk rollup protocol that is meant to scale Ethereum using zero-knowledge proofs, fully preserving the properties of security and decentralization of the Ethereum network. We were the first team to bring actually functional zk rollup to Ethereum a couple of years ago, which is now known as zkSync version 1, a specialized zk rollup for payments. But it was always the most intriguing thing to build an actually generic purpose zk rollup for arbitrary smart contracts. And this is what we started working 2 years ago, and we first introduced the concept of zk EVM in the beginning of the last year, raised a significant amount of money from a number of world-class investors like led by Andreessen Horowitz and many other big figures in blockchain space, and actually implemented zk EVM last year and opened it for the public testnet in January of 2022. So it's now running stable for a very long time, and we are going to hit the mainnet with the first ever functional zk EVM implementation in less than 1 month from now. So zkSync is a deeply mission-driven protocol. Everything we do, every design decision we take in the technical space is considered from the bigger mission of accelerating the mass adoption of crypto for personal sovereignty. So as you will see, it affected also the choices we made around zk EVM. In fact, zk EVM itself was the necessity driven by this mission, because EVM has become a JavaScript of blockchains. It's the lingua franca of the emerging Internet of Value that has so many tools, services, libraries, infrastructure built for it that it's really, really hard to escape. It's going to stick with us for a while. And zk is an extremely interesting technology that is, in fact, the only method we have to escape the blockchain trilemma, the only method for infinite scalability for blockchains that will fully preserve the properties of security for every single transaction. And the combination is obviously has to become a zk EVM. And you might have heard of a question of whether we can be merely compatible with EVM, or whether we can go for full equivalence and whether it's desirable. And some protocols are claiming EVM equivalence in what they're building, whereas we believe that this is actually a spectrum. So Vitalik has nicely put this spectrum on a graph a couple of weeks ago in a brilliant blog post, introducing several types of different approaches or like different degrees of EVM compatibility in zk EVM world, demonstrating that the higher you go on the compatibility side, the more performance trade-off you're going to be engaging in. So I'm going to give you a deeper intuition on what each of the types mean, where the performance penalty is coming from in terms of zk implementation, and what is desirable, what we will be doing for zk sync, and how it will affect the users. So we begin with the bottom. The type 4 is where you reach EVM compatibility at the source code level. You can take any source written for for EVM and run it in the zk EVM environment. Type 3, type 2.2, 2.5, type 2, all above, you add bytecode compatibility. And then the higher you go, you just add feature classes, like going more compatible on the API side, being able to support full gas measurement metrics exactly the same way as layer 1 does it, and finally being able to prove the full block root hash, including consensus, storage updates, etc. So let's explore them. Let's go let's begin with the type 4, with the the most advanced in terms of performance because it's a type of EVM compatibility where you take the existing code and you compile it into a specialized VM opcode set that we would call RISC, reduced instruction set. It's not an actual RISC, but it's very similar because every instruction is optimized to be provable in the zk EVM environment. The problem in the zk environment is that we have to implement all the constraints for all of our instructions at every step of the execution trace. So like at every step, the costs of the step for performing the zk proof generation will be the sum of the costs for every single component of every single instruction. So what you want to do in order to maximize the performance is to go and reduce the number of instructions to the absolute minimum that enables the flexibility sufficient to express arbitrary code and compile arbitrary code into this instruction set. And you want instructions to be really small, really atomic, really simple. What it means is you get orders of more performance compared to any other method, or orders of magnitude more performance. And you get the ability to experiment with innovations in the space. So you can do interesting things that affect user experience or developer experience, such as account abstraction, the ability to perform multi-calls with a single click on your MetaMask or whatever wallet you're using, or being able to use wallets like Argent or smart contract-based wallets with social recovery, etc., using different signature schemes, using native multisigs, etc. So that is on the UX side. On the developer experience side, you get an ability to bind libraries written in any modern language, which can also be compiled into zkVM by using the LLVM compiler framework, which is very mature, and front ends for LLVM are present in basically anything from Golang, Rust, Python, whatever you're using. The main downside of this approach would be that any tool that works with EVM at opcode level will not work out of the box. So we'll need to implement the specialized support for these tools. This is mainly confined to debuggers and tracers. They will need to be adjusted in order to support zkVM and zkSync or whatever protocol is using this approach. But the number of those tools is limited, so we can actually go and do these implementations. Now, this is why we're going to start with type 4 for zkSync from day one of the launch in the mainnet, because from the perspective of our mission, UX and performance are critical. You cannot really onboard millions of new users if the UX is worse than what users are expecting from modern neobanks apps or like from any kind of Web2 experience. And the performance, you need to squeeze it out to the absolute minimum, or like you need to squeeze the cost down to the absolute minimum and keep the performance absolutely high in order to unlock the use cases such as social networks or gaming or any kind of microtransactions where you need to do really a lot of transactions, where the difference of orders of magnitude will really play a role. Like it matters if you pay 10 cents or 0.01 cent for a transaction. Okay, but let's explore what comes beyond type 4. All the other categories of zk EVM that are mentioned by Vitalik, we can call them CISC type architectures. So they're using complex instruction set, which is EVM. And that means that we must support some instructions that have a very, very different cost profile. So we have two approaches that allow us to tackle this. One would be to implement native zk circuits that support all of the instructions. So at each cycle of our virtual machine, where we prove the execution trace of your smart contract, we would have to add the constraints, the implementations of every single opcode. And as you can see, there are in the EVM, since it was not designed for a zk environment, has a lot of instructions with very, very ugly, very inconvenient, complex operations that would be just like orders of magnitude, several orders of magnitude slower than, or like more work to do than having this specially designed restricted set of instructions. So that is not really a viable option. Another option would be to try to simulate the EVM opcode, like by interpreting the complex instruction set of Ethereum using some smaller micro opcodes. The problem with this is that for each single opcode, doesn't matter how complex or simple it is, like even for very basic things like arithmetics, you have to add a lot of overhead because you need to parse you need to read the opcode from memory byte by byte. You need to parse it. You need to decide what instruction this is. You need to jump to the implementation of the right instruction. You need to then deal with the operands of this instruction, load them again from memory, etc., etc. Like you're adding again, at least an order of magnitude more costs to this approach. But that is doable. Like for some use cases, it might be interesting. And if we look at performance differences between type 3, type 2, type 2.5, they are not significant because like if you have your approach to either interpretation or native running of the complex instructions, you can gas cost metering would not add much because basic arithmetics in the zk environment is very cheap, and supporting 100% of API doesn't really affect your application performance unless you're using a lot of these heavy operations that could be optimized for zk, for the zk world. But question is, do we need to stop there? The answer is no. We can actually go and starting with type 4, we can move up the stack by adding features within the type 4, within the basic paradigm that we've chosen. So for example, if we just implement a smart contract that can interpret EVM opcodes, we would make zkSync a system that supports both native, highly performant, compiled smart contracts and also the existing EVM opcodes, which would be a lot slower, but they would still work. So this smart contract can be written in either Solidity or in more complex languages like Rust, and compiled and run in the native zkVM environment using zkVM opcodes as the micro opcodes interpreting the EVM. So that is a very limited project in scope and totally doable within a few months. Now, if we want to go to the next step, to type 2.5, all we need to do is to support the full Ethereum API on the smart contract side, which would mean that we support all the hashes and we support all the precompiles. So the hashes, Ethereum native hashes such as kchuck and SHA-256, are actually supported on zkSync from day one. When we launch on mainnet in less than a month, they will be already there. So all the contracts that are using kchuck, using SHA-256, will be producing the exact same results as they would be doing on layer 1. And all the other precompiles, we expect them to be complete by the end of year. So the most complex part will be implementing the support for elliptic curve pairings. And the work on this is already started, and the rest is kind of simple and already supported. So doing those two things, adding interpreter and adding the 100% support for the API, would make zkSync a type 2.5 system. And it's really interesting to notice that if you start at the bottom, you can always go up. if you start with a more performant, more advanced system, you can always simulate a system that is less performant. Just like you can simulate older versions of macOS on a modern MacBook, or even go back and simulate some mainframe or MS-DOS, or like earlier Unix implementations. But you cannot really do the other way around. You cannot take the old system and try to simulate a modern macOS on it. So you can really go only in one direction. So you have to start with the most performant option. So okay, so we are at type 2.5. In order to go higher on the compatibility scale, we would need to support the exact same calculation of gas as Ethereum, and support the storage and consensus compatibility. That would be counterproductive for L2s. That would make sense to be able to prove Ethereum blocks themselves, but that really doesn't make sense for L2s. To understand why, you have to look at the cost profile of operations between layer 1 and layer 2, and you will see that the resources are priced differently in layer 2, and this is what enables scaling. So bandwidth would be roughly the same. If we're talking about roll-ups, it's going to be like basically exactly the same. But the computation in layer 2, specifically in the zk rollup environment, is extremely cheap. It's much cheaper than doing the computation on Ethereum that has to replicate across tens of thousands of different machines. Similarly with storage is extremely expensive because you have to run to do it on like all the full nodes of Ethereum that have to maintain fast read-only access to SSDs. And with layer 2s, you don't really need that because the zero-knowledge proofs verify the storage updates. The users only download the hash and the state deltas, and it's going to be a lot cheaper, especially for Validium, for all kind of Validium implementations, including zk Porter. So if you were to support the exact same approach to gas metering as in layer 1, you would be shooting yourself in the foot, because either you are not getting the gains of the performance optimizations that are possible at layer 2, or you are opening yourself to kind of denial of service attack vectors if you misprice your resources. So this is why we believe that there is really no need to go up higher on the compatibility hierarchy, and we think zkSync will stick at type 2.4, and going higher for Ethereum also, in my opinion, doesn't really make much sense, because you can, if you want to make Ethereum full node verification cheaper, community can just decide to reduce the block size and make the storage really expensive in layer 1, and only use layer 1 for actually verifying the validity proofs, fraud proofs maybe for zk and optimistic rollups, and everything else, all the applications should be pushed out into the L2 space. And this is how we expect things will be happening. So like there is only marginal upside in going into full EVM equivalence by supporting the type 2 and type 1 EVM systems. And that is the end of the presentation. I hope it was useful, and thank you again for inviting us to the Global Blockchain Summit.